In this video I want to explain an application of integration which allows us to calculate the volumes of objects called solids of revolution. So I'll see how much I can get through in this video. Don't want to bite off too much, but might have to go to a second video to get through all of this. So first of all, what is a solid of revolution? And a solid of revolution is something that we can obtain by rotating a curve around an axis. And so in our case, we'd either think of rotating a curve around the x-axis or the y-axis. So let's maybe start by thinking about some sort of curve here, or a part of a curve which is continuous. Let's say this was the function y equals f of x, and we're just considering it from, x equals a here to x equals b over here. Now, if we took that curve and we rotated it about the x-axis, we would form a volume, or rather a solid, which, was something, I guess, vaguely resembling a cylinder. But rather than having a straight edge, it's going to have an edge which sort of varies. So try and think of, for example, at the point here where that distance there is f of b. Okay, so that distance there would be the value of the function at x equals b, so f of b. So if we took that same distance and we rotated it around this point here on the x-axis where it's sort of anchored, then we would kind of get this curve that's coming around to a point down here which is also a distance of b, and anywhere along here, all of these distances here would be b, and then we'd keep going around the other way and back to where we started. So anywhere we measured from that point out to the edge of this would be a distance of f of b. So what we're doing is every point on this curve, maybe let me grab another color, so this point here, we're going to take its, I don't know, maybe that's, let's say c, so this distance here would be f of c. So that same distance, we're going to sort of anchor it here on the x-axis, and we're going to rotate it, like swing like a big arm, I guess, kind of swinging around to the bottom and then back up to top again, and all of those distances there are going to be f of c. So over here we'll have, f of a. We're going to take that and rotate it around and then back up again. And so if you can sort of visualize this in 3D, then we can say, well, that'd actually kind of be a, let's see if I can, don't know if that's terribly accurate, but there it is, sort of mirrored down there. And in fact, it's a three-dimensional figure, a solid. And so that's a solid of revolution, and we're going to try and use integration to find the volume of that solid of revolution. So I want us to think about the fact that we could, as a way of approximating this volume, a little bit like we approximated area under the curve by breaking it up into sort of rectangles, we could actually approximate volume by doing a similar thing. So rather than rectangles, we're going to take sort of discs. So I could say I go along a little distance at the top and the bottom, and I actually get the other part of the disc. Let me just try and draw it down here again. I've got this sort of disc like that, and maybe we could draw a dashed line in there so we can visualize that. So I've got this kind of really, I guess think of a coin or something that has a very small height. And we're going to break the whole thing up into discs, so I could do another one, down here, sort of a disc there. And likewise everywhere along this curve, I'm just breaking it up into a whole series of little sort of narrow discs there. And each of those discs, I'm going to say, just has a small width or height, if you like, of delta x, so some small change in x. Now what about the area of the base of that? So this is a cylinder, so its base area, the area of this circle part in here, well, it's going to be pi times radius squared isn't it? So the area of that part is going to be pi times radius squared. And remember we said the radius squared is just going to be the value of the function at that point. So for this end one it was f of b. But at any given point it's going to be f of x is going to be the radius. So I'm going to need to do pi times radius squared, which will be pi times the value of f of x squared. That'll give me the area. So therefore the volume of each of these disks will be pi times the radius squared times the height, which is delta x. Now I should really, rather than saying equals, I should really say approximately equals, because obviously this is only an approximation. And so the way that I could get the approximate area of the entire solid there is to say, well, therefore the total volume is going to be approximately the sum of all of these disks put together. So let's say that I said the value of x at this first point at x equals a, that was x naught, and the value of x right at the end here at x equals b was x sub n. And so all the little spaces that are separated by delta x, they just have sort of an incremental value. So this next one here is x sub 1, and then I go another distance of delta x, and that's x sub 2, and x sub 3, and so on all the way up to x sub n. Okay, so I'm taking the sum of all of the volumes of these individual disks, which all have that form there, and I'm going from I equals 1 all the way up to I equals n. So for the first disk, I'm using f of x sub 1 as my radius, and for the last one I'm using f of x sub n as my radius. So that's going to give me the approximate volume. Now, just like when I was thinking about area under the curve, and I was saying, well, let's use all these rectangles, and the way that I could sort of come to the exact value was to take the limit of the sum of those rectangles as the width of the rectangles approached 0. In other words, as I got a kind of infinite number of rectangles. So here I'm going to say, well, therefore the exact volume would be the limiting sum. So the limit of this sum, I equals 1 to n of pi times f of x sub I squared delta x, the limit of that as delta x approaches 0. In other words, as the width of these becomes smaller and smaller. Because if delta x is large, then approximating the edge of one of those with a straight line is not very good, because it's probably curved like this, and I'm sort of doing this, not a straight line, let's go, I'm doing this kind of disk, and I'm approximating, the edge of that disk with a straight line when in fact it's curved. But as I let delta x get smaller and smaller, then the fact that this little section is curved, because it's such a tiny section, actually a straight line is a very good approximation to that. And so it's the limit as delta x approaches 0, and that is the integral over the sort of domain from x or I equals 0 to n, which in other words is from a to b, of pi times f of x squared delta x. Okay, so we didn't really spend a lot of time developing that when we did our area under the curve, but that's really what the integral from a to b of that function just means, the limiting sum of that as delta x approaches 0. Now, because the pi is a constant, we can actually take pi outside the integral and say it is pi times the integral from a to b of f of x squared dx. That's a formula that is on your formula sheet, okay, and that is for the volume of a solid of revolution when a curve y equals f of x is rotated around the x-axis. Now you don't need to, remember or know any of this way that it's developed. You do need to know and be able to use this rule, but as I say, it is on the formula sheet, so in that sense you don't need to remember it. Now, just before we go on to doing an example, we should point out that the curve could instead be rotated around the y-axis. So we could have sort of some part of a curve and it's kind of being rotated around the y-axis so that we're getting a volume or a solid formed that way there. And in that case, and I won't go through sort of all the working out, but we could say now we're talking about y going from A to B, and these radius lengths here, if you like, are now x values, which are, so this curve here, I would say x is a function of y. So I'd need to make x the subject, express it as a function of y, and then I could just write all of this in terms of y. So really the same rule, if you like, but now we're expressing everything as a function of y and an integral in terms of the variable y rather than in terms of x. And that formula is also on your formula sheet, so you don't need to remember that one. So let's go through and maybe just do a quick example. And I know this video is going to go for a little bit long, but then there is one other sort of application of this that we need to talk about. So let me just pick, I'll just pick a question from the exercise. So exercise 12D. We're talking here question 2a, and we've got this function f of x equals root x, and we're also given the function x is equal to 4. So we're trying to find the volume of the solid that's formed by rotating that region, the region bounded by those curves, around the x-axis. So they look like y equals, or f of x equals root x is just kind of like that. So here's, let's say that's x equals 4, which is, you know, just a vertical line, isn't it? So there's y equals root x, there's x equals 4. So we're just trying to rotate this region here around the x-axis to create a volume there, or a solid, and find out its volume. So our rule is volume equals the integral from A to B, that's the domain of the curve we're rotating, of f of x, since we're rotating around the x-axis with respect to x. So that's going to be, and really the x equals 4 just gives us the upper bound of the integral, doesn't it? So we're going from 0 to 4, so there's 0, there's 4. So 0 to 4, the curve is root x, and I should remember my pi in there, that's important, isn't it? So pi times, well, this one kind of works out nice and easy because the square of root x is just x. That's going to be equal to pi times, what's that, x squared over 2, 0 to 4. So it's going to be pi times 4 squared over 2, so 16 over 2 is 8, minus 0 squared over 2 is 0. So that's going to be 8 pi. Now, because this application is for volume, if we're not given any specific units, we should just indicate that that is units cubed. Alright, enough for this video. There's an introduction to volumes of solids of revolution.